Hello everyone. It's April the what? April the 2nd. All right, April the 2nd. Let's do this today. We had an easy one yesterday, kind of boost our confidence. So let's see what we have today. Ones and zeros. Ones and zeros. Okay. You're given an array of binary strings, these are binary, and two integers. Return the size of the largest subset of strings such that there are at most m zeros and n ones in a subset. I said x is a subset of set y if all elements of x are also elements of y. Okay, the size of the largest subset. The largest subset with at most 5 zeros and 3 ones is 1, 2, 3, 4, 5, and 3. So the answer is 4. Other valid but smaller subsets, yes, yes. This is an invalid subset because it contains 4 ones, greater than the maximum 3, okay? So 1, 0, and 1, 1. So this can't be 0, 1, because this one is only 1, right? Okay, so we have 600 of these, and each one, the length is smaller than 100. It's only 0 and 1, and then it's 100 or smaller. Okay. So the maximum, we have 600. I mean, we can loop through first to eliminate the thing that we cannot include. For instance, if this, we can loop through, eliminate these, right? They cannot be. And then we are going to loop through again. So we need to know how many zeros and ones there are in each position, right? So let's just say it's going to be, say, I'm not gonna say dictionary. I think it's gonna be like 2D array, right? Let's look at this example. So we say it's gonna be a 1, 2, 3, 4, 5 by 2, right? 1, 2, 3, 4. A 5 by 2 array. Each row is an index. Each row has an index, and each column is, the first column is the number of zeros, and the second column is the number of ones. So the first one, what we have is 1, 1. Second one will be 3, 1. Third one is 2 zeros and 4 ones. And this is 0 zeros and 1, 1, and 1 0 and 0 1. Okay, so that's what we get. So the question is, we're gonna find the maximum rows, which means the maximum number of rows whose sum on the first column, the 0 column, adds up to a value smaller or equal to m, and the second column adds up smaller or equal to 3. Now, smaller or equal, when we add them together, we can find, I mean, if we do it in a greedy sense of way, we want to make it as big as possible, the total number of rows. So we want to find the ones that that's really small. Like we need to find the one that has minimum, right? So for the column 1, we want to find the minimum. So the minimum to go first, like 0, right? For column 1, we have 0. For column 0, we have 0. So we can sort them, but we cannot consider them individually. We have to consider them as a grouped together, which means we might be able to sort them. We can sort them based on the sum of the two columns, right? Because we want small numbers on 0 and the small numbers on 1 for each row, because then we can add them together. If we have a giant number, like we have a small number on the count of 1, but a giant number on the count of 0, that one will be useless. So we need to balance the two, so we can say we add them together, right? We add them together, and we can do a sort, right? We do a sort by add them together. So let's say if we sort this and add them together, and we don't care, so we're gonna say 0, 1, 2, 3, 4. So it's 3, so we have 0, 1. 4, we have 1, 0, they will go first, and then 0, we have 1, 1, and the 1, we have 3, 1, and 2, we have 2, 4, right? So that's after we sort. And then I want to see, well, we have to pick some, right? We have to pick either, because m and n is larger than 1, so we have to pick at least 1. Or at least actually, yeah, at least 1 we have to pick. So we pick 1 on the smallest side, and then this will give us, you know, we would pick that, and that will give us, we reduce m and n. So if we pick this, it'll give us m and n. So in here, we're going to pick this or this, give us m and n. So I'm going to decrease, we'll pick the next one. Decrease, so we'll pick the next one. So the question now is, if the sum of the two is the same, right? But then there are different ways for them to be the same. So what we want is for them to be as equal as possible. Can we force that? Can we force that? Or we don't think like this. We think of picking the maximum numbers, right? Picking the maximum numbers that satisfy 1, and then we pick maximum number that satisfy 0, the requirement on 1 and 0, and then we lay them out and see if any of them overlap. That will be that might not be straightforward. I mean, some of the two might not really be a good idea, because if I do sum of 2, I can bias, right? I bias on 1. So we can sort based on their sum of the count of 0 and 1. So the smaller goes first. And then if they're the same, we sort by the difference of the two, right? So the difference of the two, the more difference means that's more skewed, then we don't want it. We want it to be more evenly distributed. Oh no, that's also depending on the m and n, right? That depends on the m and n. It's not strictly, no, it's not strictly saying like it's evenly distributed is better for the 0 and 1s. Between m and n, we can find. Let's try the. Let's go back to the method if we want to go for the smallest, right? So n is 3. So we need to have 3 1s. So we're looking at 1. To get 3 1s, the maximum we can have is 0, 1, 2, and 0, 1, 3, and 4, right? So 0, 1, 3, and 4. So when we do that, we can add up all the zeros. So 0, 1, 2, 3, so I'll add up to 3. And for the zeros, we add up to 1 plus 3 plus 1. This one satisfies already, so 4 is the answer. How about this one? Yeah, this one will be interesting. So this one will be a 3 by 2 matrix, right? And then the first one will be 1, 1, second one will be 1, 0, third one will be 0, 1, right? So m and n has to be 1. So so we can have is then we have different, right? We can do like 0 by itself, or 0 1, or 1 0, right? Or 1 1 2. So I can do this by itself, but then there are different combinations of this. But note that there are only 600, right? There are only 600 of them. Well, 600, maybe we can do combinations. Maybe it's not unthinkable of running a combination on this. Well, we pick the smallest first, right? And after we pick all the smallest, well, we pick the smallest first, and then, let me think, if we pick all the smallest, well, the smallest will be zeros, right? Zeros. If we pick the smallest, and then if we pick the smallest, and then we pick like ones, and then we pick two, like that. So we can accumulate a list of values that will make it work. It's like filter. Like, I'm just thinking if that idea is actually feasible. We pick the smallest first, which give us 0, right? That's the smallest. And then we need to pick the next one. But then the question is, we have different strategy to pick. Anyway, we need to eliminate the ones that don't belong. That's for sure. Right? That's for sure. We need to eliminate the ones that don't belong. So we can kind of shrink our size. And then most 5 and 3. So we know the numbers. And what's the maximum number of ways, right? Maximum number of ways to achieve this. To achieve this. That seems just to be the same question, right? You have, basically this means you have different weights, and then we want to find the maximum ways of putting these items into a knapsack. Isn't this a knapsack problem? Yeah, I think this is just a knapsack problem, a modified version of a knapsack problem. That's why it's so small, because if it's bigger, it's unsolvable. Like it'll take a long time to solve. How do we solve knapsack again? I actually forgot. Do we use greedy to solve it? Like we put the ones that's the lightest, and then put the one in it. Like do we? Okay, so can I use like dynamic programming for this? Like if we sort it, right? If we sort it, and then we say we have the smallest at the front, and so we put this one in. So if we have that much, then this is the maximum. We're going to be putting a 1. We have 2 for each one. The decision is either we can put into it or we don't put into it, right? And if we put into it, it doesn't blow up, then we say, is this have the maximum sub problem? Like if I have a list of items and I find the maximum number of items I can put into it, and we can now put another one, and I have a new one. Can I put that one into it? Or like if I cannot, so for any item, right? For any item that I want to put in, if I already have some items in it, right? So yeah, so if I have already some items into it, and which is the maximum, I already know for a certain number of items already. Now I want to put a new item in it, and I can check if I can put into it, then I do it. If I cannot put into it, then I can see if I can swap it with something that's already in it, right? And I want to swap. Like if I swap it, I can reduce the total weight. It's like the total, yeah, if I can reduce m or reduce n, if there's a reduction, the maximum reduction that I can achieve by doing a swap, then I swap it, right? So in that case, we probably don't need to sort. So for instance, we still have to do this binary table, table, I think. And what we do is for this, right? The goal is 5 and 3. So we have the first one, 1 and 1. So we put in 1 and 1. We can because initially 5 and 3. So now 5 and 3 becomes 4 and 2. Next one is 3 and 1. 3 and 1 we can put in. So we put in 3 and 1. So it becomes 1 and 1. Next one is 2 and 4. We cannot put in. 2 and 4 itself is exceeding this. Actually, we can check this first, and then we just know it cannot be put in no matter what, so we ignore it. And then we put the next and put next. That's good. For this one, yeah, this example is actually not really good. It doesn't have any twists and turns. Let's look at this one. We start with 1 and 1. The first one we have is 1 and 1, so we put it in already, and we satisfy, and then it becomes 0 and 0, right? The requirement is 0 and 0. Next one is 1 0. We have 1 0 and a 0 1. So 1 0 coming in, and it satisfies. And but if we want to put in, that become 2 and a 1. It blows up, right? Blow up. So what we can do is we replace. Go from front. We try to see replace and see if we can maximize m or n. So we replace. We only have one thing to replace with the first one. So we replace it, which now becomes 0 and 1. And we have achieved n. We actually get n bigger, so we say that's good, right? That's good. And then finally we add another one. Maybe let's try this. Let's try this idea of replacement. Replacement. Okay. Not sure if this replacement idea can work, but seems logical to me. Seems logical to me, right? I think it's logical. We basically are saying that every time we encounter a new item, we determine whether by adding this new item into our current bag, it can either be added to increase, which is good, or it cannot be added because it exceeds the requirement already, so we don't consider it. These are trivial cases. And in next cases, we want to know which one that's currently in the bag can be replaced, because we say that the one current in the bag has already maximized the remaining of m and n. And if we can replace it, then we're giving us more opportunities to increase, to add a new one later on. So I think this one might work. Not 100% sure, but it might work. So we're gonna do items equals. So this is gonna be this, and it's gonna be this. And for s in strs, right? So it's going to be s.count 1 times 0 and s.count 1. Yeah, I mean this is gonna waste some time, but only 100, so that's fine. So that's all the items, right? And then we're gonna try to maximize m and n at each run. So we're gonna say for it in items. No, we're gonna say for I and count 1, count 0. No, count 0, count 1. Right, so it's going to be like this in items, enumerate items, all right. You know what? We actually don't need to do it this way because we are replacing. So let's actually, we can just do count 1 and count 2 because we need to push count 1 and count 2 into the result. So we have res equals this. So we have count 0 and count 1 coming into it, and we say if count 0 smaller than m and smaller equal to m and count 1 smaller equal to n, then we say res.append count 0, count 1, and m will be decremented by this, n will be decremented by this. They're decrementing, so I don't want, so I need a new one to say current n equals mn. So I don't need to, so I have the original to refer, right? So current, and then these will be muted as we're going through. So this is the first one, and elif, let's say C0 is larger than m, or C1 is larger than n. This is a trivial case, which we just continue. Right, that's a trivial case, which we just continue, we don't consider it. Now this is where the money is. The money is we cannot add directly, and it does fit the original. So we need to go through everything in the items again. So I'm going to say, right, what we're going to say is for item in items. No. In result. Let's call it C0 underscore and C1 underscore, kind of just identify them, right? So what do we want? We want to know which one we shall replace, right? Can result in the maximum gain, right? So we also need to know, so we need to know the gains for m and the gains for n. What if the gains for m is larger, is like, what if we have a situation where the gains, after we incorporate this, the gains on m is big, but the gains on n is small, versus the gains on m is medium and the gains on n is medium. Well, I think what we need is to find one has the minimum gain, what we want to find is the minimum gain on both m and n, because the minimum is going to be, like, you can't have m gigantic, right? You can have a gigantic gain on m, but n has a tiny gain, right? And then we're gonna blow up on n, and then even though your m have gigantic, it doesn't really matter. So what we want is to achieve a maximum, not a maximum, let's do that again. So as we go through the ones in the result, we know by each replacement how much gain we can have on m and n, right? And then eventually the ones that we're going to replace, will be the one that have the maximum gain. So let's do this again one more time. So as we go through them, we're going to have a gain on m, we're going to have a gain on n, right? And I'm going to take the minimum of the two, right? Take the minimum of the two. And what we want is to find the replacement that can maximize this minimum gain. And then we're going to swap with that. And if we go through, the minimum gain is, say, negative, which means we cannot gain, then we do not swap. Okay, so that's the idea. So we're gonna have is maximum gain on the minimum between m and n, right? So maximum gain, we're gonna set as 0. So I'm gonna go through this. Actually, we also need another variable. So maximum gain, and what else? Another one is index. So when you know which one to do, so I'll put index -1. So we need I. So I'll put this in a enumerate, right? Okay. So as we go through, we compare C0 and C1. How do we compare? So we're gonna say gain m. Let's call it m gain equals what? So which means we take it out, which means we give it back. So current m gain will be current m. This is the current one, and then we do the swap and we're in the new one. So it should be the new one minus the current one. So it's gonna be the new one. I don't know how that is, but we know that it's gonna minus the current one. So the new one will be the current one first. We're gonna give it back, right? We'll give it back this, and then we adding this. All right, give it back, add new one. So that's the current. That's the m gain, and we also have the n gain, which is, that's actually not correct. It's a C0, and here is C1. So giving back the 1, and then we deduct the current one, right? So we have this, and I'm going to say if we say max gain is smaller than mean m gain, m gain and n gain, right? If the max gain is smaller than this, which means currently by swapping we can achieve more max gain, and then we say index equals I, and max gain equals this, right? And now we run through everything, and I want to check if max gain is larger than 0, right? It's larger than 0, then we swap. How do we swap? We say res index equals C0, C1. We are swapping. Elsewise, we don't swap. So after we go through everything, and then we can just return len res. Okay, I think this will pass the test case, but honestly, I am not comfortable, not really confident. I shouldn't say comfortable. Confident in the actual result. This feels like one of those questions that I can get stuck with. I had a stuck feeling already, but hey, doesn't matter because we already set the rule. The new rule is 45 minutes. If we don't see the light at the end of the tunnel, we're gonna call it. So far, I still see the light I see lots of light actually, and we hope that this one will come to fruition. Okay, so this one will have 1 and 1. Oh, I didn't count the result. The result is 4. This result is what is this result? 2. Okay, so we're gonna do this is going to be strs m and then this one will be find max form strs m and n. See these two? We're not successful on these two already. We passed the first one, which is understandable, but we failed on the second one. How is the second one failed? All right, we'll see. Okay, let's first check on item, see if item is correct. Item is correct. So I'm gonna go through here. The first one does, and then we do this, and then see our current n becomes 0, coming back up. Oh, we say it has to satisfy. No, it doesn't satisfy this because current is smaller. No, it doesn't satisfy here, and then it's larger. They're not, right? It's 1 0. It's larger, or what happens? So it doesn't. So we have to go here. So we go through here. Let's see if this one's entered, right? Let's try. Let's see this one is entered. We shall see. Yeah, it is entered, but it's entered more than once. That is strange. Oh, I know why. Because after we do this, we forgot to update on the current m, the current n. Okay, so how do we update? So we say current m. So we have to update. Current m equals current m plus less index 0, and then minus c0, which just means this is plus equal to, right? So plus equal to this, and current n plus equal to 1, 1, and then we swap. That is still not correct. I am not sure. Let's do print current m and current n, see if anything interesting happens. They all become 0, even after we do this. So is the max gain is not working? All right, let's see the max gain. So currently, I can't actually do it on paper. Currently, we have 1, 1 in the result, right? So currently, 1, 1 in the result, and then this will be 1, 1. So the max gain. So currently 1, 1, and we are pushing in. We're trying to look for 1, 0. So we have 1, 0 coming in. Yeah, 1, 0 coming in. So we say maximum gain on m. If we swap it, will be current m is 0, current n is 0. So it'll be 0 plus this is the 1 minus 1 is 0. M gain is 0. And oh, that is the problem. We say the maximum gain on the m is 0, but the maximum gain on the n, because this one is 0, and this is 1, and this is 0, so this becomes 1, right? So the n gain is 1. Then our theory is not correct. So the gain on m is 0. So by swapping, we don't gain on m, but we do gain on n. And then in that case, we say the maximum gain, then the minimum is 0, right? So we do not swap. Yeah, so what is the swapping criteria? So we swap based, so we have the gain, right? So after we swap, we can increase on m and increase on n. What we want to do earlier is saying we want to have the swap and it can increase the minimum on the gain. But if the minimum on the gain is no gain, right? So it's no gain, but no gain is still, it's a gain. Like on any one of them, it's still a gain, right? It's still a gain. But which one do we pick? Well, which one do we pick? Do we pick the one with a maximum? And that's not right, because we already can think of a situation where if you pick the maximum gain, that's not going to work. You pick the one with a sum, that's also not going to work. How do we pick? Or you just don't pick. You just, because if I swap this, I can have some gain, right? We increased on m and increased on n. And then we swap on another, we can do this increase as well. Now, which one do I choose? Which one should be the, if we do a maximum, right? The maximum gain is, if we say m plus n, right? The maximum gain on both. Then I can see a situation where we're going to fail. Because we can just put, but anyway, so something that put inside, right? If we have a max gain that's on, like maximum gain on one, but it does not have a good gain on the other, that's still, isn't that still good versus a gain that's evenly spread out. Evenly spread out. I have this and that evenly spread out. If the gain is evenly spread out, that doesn't really mean that it has benefits, because it depends on the original m and n value. So we want to swap, right? I come back to the idea. So every item coming in, we can go through the ones that's already in the bag, and we decide which one we want to swap out. And if we swap it out, and we keep swapping out, can we like just put it at the end of the items again? So every time we swap out, right? Every time we swap out, we put it back, so we give another chance. Like if we made a mistake, we can go back to put it back and try it again. And eventually, if we have come to the best solution, then it shall stabilize, right? The things that come out, they shouldn't come in again. I cannot swap anybody out again. That's another idea. So here, what we're gonna say, yeah, let's just do the sum. It's like a proxy here. We just say, we're gonna say sum on this, right? And then we say it's gonna be the sum. But there is a possibility that the ones that we swap out is going to be bad. So we're gonna say old C0, old C1 equals res index, and then this one gonna be old C0. This will be old C1, right? Old C1, and then rest this, and we're gonna append. We're gonna say items dot append old C0, old C1. I'm not sure. We might run into forever loop, but I think I can append it back because every time we swap, we put it back because we might be able to do that again, right? So this one will pass, and this one will pass as well. We put it back and then try to do it again, and then we find out that there's no more gain. So if it's no more gain, then we basically say that's it. Let's try this. Yeah, not very sure, but we can try. See how it goes. At least we need to try. Ew, we have a wrong answer. Output a 1. Expected 3. Yeah, I think we're entering this already. Let's see. Even with our modified version, it's still not doing very well. Okay, no panic. Still have some time. Now I'm gonna keep going today because just so that we work out the solution completely. Something wrong? Oh, we didn't put answer. Expected 3. We only get 1. How? What happened there? Okay, so same thing. I'll check on the items. Items good. Let's go through it manually. So what we're gonna do is we put 0, 3 into it, right? We put 0, 3, and then this become 9, 0, M&N. And next we want to put 3, 1. No, it doesn't work. So we try to swap. So swap out is we swap on the first. Our gain is our gain is because currently is 9. 9 minus 3. Our gain is minus 3. So the gain is minus 3. So basically we say this. Okay, let's just do max. All right, let's do max. We want the max gain. As long as we have gain, we say let's try it. Right, let's try it. Oh, this gives us forever loop. How this gives us forever loop? So we always have. Oh yeah, this always have gains. Because the first one we're gonna have a minus 3 on the gain on 0, and a plus 1 gain on the plus 1 gain on 1, and then we say it's a gain. Say we're gonna do 1. So we swap in, so this become 3, 1. Right? We say we do 3, 1 and put 0, 3 at the back. So I'm gonna have another 3, 1, another 3, 1. So we're doing a 3, 1. So this becomes 6, 1. Right? Man. Oh yeah, that's because after we add the 3, 1, 3, 1, 3, 1, and then we add a 0, 3. So we add 3, 0, 1. Already give us 9, 3. All right. We add all these 3. They give us 9, 3, and then we add 0. We'll try to do 0, 3, and then the remaining is 0, 0. So we go to the front. We say, how about I swap out a 3, 1. And by swapping out 3, 1, I have minus 2 on 1, and I gain. I gain 0. So the current is 0. Both are 0, and then 0, 0 minus. Oh, that's 3. Right? 0, no, this is 3 minus 0, so it's 3. So we have plus 3. Yeah, we have plus 3. We have plus 3 on the ones. Do I just not put this? We just pick the maximum, and no, I think this is I don't think this is gonna pass. I pass all these, but I don't really think so. Well, we can try, but it's not stable, right? Basically, that's what it is. It's not stable. And we pick the maximum, and we pick the one that gets the maximum gain. I don't feel this is stable though. All right, try it again. Here. Yeah, I feel this is not stable. So this is gonna fail. Yeah, this is gonna fail. Oh, we have a standard output. Ha. Expected 4. I think it's because it's not stable. Yeah, put this on this. This is 1, 2, 3. 2, 3, 4. Yeah, in our case, we have 7, 6 to begin with, and now we push in 2, 2, right? And then this becomes 5, 4. Then we're pushing 1, 6. Oops, we cannot push in 1, 6. So we try to swap. So if we swap, and then we always have gains if we swap, right? Because if we swap, swap on the first, what do we get? So we become 5 plus 2 minus 1. This is gonna be 6, right? And then 6 minus 5. We're gonna plus 1, right? We gain 1 on the 0. And the second one will be 4 plus 2 minus 6 will be 0. So our overall gain is 1. So by doing the second, we're gonna gain 1. So I say I do it. If I do it, what we end up with is, because we do 1, so it's gonna be 6, 0. All right, 6, 0. We gained. How do we gain only 1 on the? That doesn't seem right to me. Maybe I didn't calculate it right. So the current n is 4, right? And then current n is 4. And by adding this, is 6 minus 6 is 0. So minus 4. We have minus 4. So we're going to lose 4, and then we gain 1. That doesn't seem to be a good deal to me. But we tried plus, but plus doesn't work. Plus doesn't work. So basically we go from 5, 4 to 6, 0, right? 5, 4 to 6, 0. So we gained 1 on, yeah, that doesn't feel like you should do that. It doesn't feel like you should do this swap. Why is it not good? Because why the plus doesn't work? Well, the plus doesn't work because, let's go back to plus. I feel like plus sounds better. Plus sounds better here. Let's just do plus. I feel like plus is the only way to consider both. Because if you do like maximum, minimum, and then we're gonna fail on some of these. Hold on. The plus works, but doesn't work on the last one. Wait, how does the plus work on the first and the second one. Isn't the plus fail? What did we do differently? It fail on the last one. 0, 1, 2. Oh, yeah, it does fail the last one. I haven't added this one yet. Okay, let's add this one. Here. It's hard to judge. I still think there's a hope. We just need to tweak a little bit. Just a little bit tweak. We might get it. I forgot about answer. Answer is 4. So the plus, we fail on the third one, right? We do understand why we fail on the third one, because the original, so we have a gain, right? And what we say is if the gain is smaller than 0, because by doing 0, 3, and then if we do this, the plus on this side and the minus on this, we are having more negative. We have negative gains. Because why do we have negative gains? Because initially we have 9. Yeah, we have 9. So the gain on here, do we do percentage gain? How about percentage gain? Right? So like percentage gain. So we have 9 to start with on the 0. So 9, 3, right? After we do 0, 3, we result in 9, 9, 0. And then we have 3, 1 coming in. So 3, 1 would have resulted in 6 and 2, right? And 6 and 2. The percentage decrease, right? 6 and 2. The percentage decrease or from the original, so is 3 over 9 percentage. So the or actually just the percentage. Yeah, we should use the percentage. 6 over 9 is the percentage. How should I say it? The percentage, like after we swap, right? After swap, this is the percentage that's been that's left. The percent that's left, right? And then there will be 2 over 3. That's the percent that's left. But if we do 9 and 0, the percent that's left is 9 over 9 and 0, right? 9 over 9 is 0. So, which is 100% left on the 1, but 0% left on the 0. So we do multiply. We multiply them, right? We multiply them. Let's try this. This is definitely a weird way of doing it. So instead of calculating this, we say percent gain, not percent gain, percent remain, right? Percent. What's the percentage? Or it's a likelihood. It's actually a likelihood, right? The likelihood that you can get another one. The likelihood percent remain. Percent remain is fine. So we're gonna say, what do we say? The original. No, it's just a comparison. No, we also need to see which one is the maximum. It's actually the max remain. Max percent remain. Max percent remain has to be larger than 0. And then we say old, right? Old percent remain. What's the old percent remain at that stage? Well, the old percent remain, it has to be, because it's not the current m, right? It's not the current m. It's by itself. We can just consider swapping, like not using current, right? We're using the original. Yeah, we're using the original, and we just see the percentage remain. If this one still doesn't work, we're gonna check the result. So what we're gonna do is we're gonna say gonna be m, right, minus c0 divided by m multiplied by n minus c1 divided by n. And yeah, right? Divided times this divided by n. This is the old percentage remain. So like we use this, that will result in the percentage remaining, right? And then we can also do the new, right, percent remain is going to be m minus c0 divided by m times n minus c1 divided by n. Actually, this one I can actually put in here, right? This is the new percentage remain. And but that doesn't make any sense actually, because how do we? Then there's no maximum. Then we just go through it and then swap out the ones. No, we have to swap out the ones that's the smallest, that has the smallest percentage remain, right? So we go through and then find the smallest percentage remain. The smallest percentage remain, and we swap out the ones that give us the smallest percentage remain. I actually think we can do it differently, right? We can actually have, every time we append, we can also add to it the smallest percentage remain, which we can also use for a, what I'm thinking, we can use a priority queue for this, but for now, let's just focus on this and see if we can get it to work. So we know the percentage remain is this. We just need to know the smallest percentage remain. So we can have another one. We can call it percent remain, right? Percent remain. So every time when we push something in, we get the value of percent remain. Just after we put this in, how much will be remaining, the impact that it will have on the total. Yeah, because it's linear, so it doesn't really matter. So we're gonna say percent remains, right? Remains. We're gonna do it here. So every time we can do this. Press .append, and what are you doing, man? I'm gonna say percent remains .append. Append this, right? Remain append, gonna be this. I need to know your index. I need to know your index. So it's gonna be this. Enumerate items. So I need to know your index, and this. This is your percent remain, right? Your percent remain. Let's call it impact. Call it impact. This is the impact you have when you add to it. And we want someone that has a big impact, which means have a big impact. So this is the impact. And if this, what we have is, this is our new impact, right? A new impact. And then we're gonna swap out the one that has the least impact, right? I'm gonna say least impact. Hold on. If we have, I don't even know. Can we do? Yeah, I think it's actually, we can directly use priority queue, right? From priority I forgot. What's the syntax? Python priority queue. I think it's PQ, right? Head P, head, heap queue. So we just import, right? Import heap queue. Then we can do. We don't have the heap. We can just do heap queue dot heap push, right? And this is a min heap. And this is a min heap. It is. Our pop method to the smallest, and then it will always pop the front. So we just push heap will be impact. Pushed items is going to be this, right? We're going to put this one first because this is the key, right? The one that we want to do comparison like this. And then we're going to say old mean impact. So the index old mean impact equals heap queue dot heap pop heap impact, right? Old mean impact. And then we're going to compare to see, when I say if new impact is larger than old mean impact, then we do the swapping, right? Then we do the swapping, which is this. And then we say, well, actually, just directly we can use this, right? So this is going to be 0, this is going to be 1, and then we're going to do this, and then we're going to say heap queue dot heap push impact new impact. All right, no, has to be this. What's the current I? Right, I. No. New impact I. Right. So this is the current one. He push a new one. If not, right? If not, then we're gonna heap queue dot heap push index impact, and then old mean impact and the index. Okay. Not sure. Like if this one fails, then that's it. We're going to the result page. What happens? Say list size must be integers, not float. Oh, got it wrong, man. Index is the second one. This one passed. Oh, I'm very nervous. No, it's not working. Alright, that's it. I'm going to check the answer. I am not sure. Does that work on the last one? It does work on the last one, so it's just this one. Is that impact is 0? They're all 0? I mean, the first one, the impact is 0, right? Now, the first one, the impact is 0. And then if we swap, the impact is 0 as well. Damn. How do we accommodate that? So whenever it's 0, we can tune it to like say a small value. So instead of it's not completely 0. How do we tune it? We're gonna tune it. We're gonna add a upsilon. Like we're tune it 0.001, right? This is ridiculous what you're doing right now. Like totally ridiculous. I don't even know what you're doing, man. Plus epsilon. Right? So the ideal is if we do an epsilon, that will make it will pass. Yeah, it will pass because if you have this one will give us both zeros, and then it will give us a smaller. Let's try it. Okay, let's just try it. And oh, I am almost certain this is not going to work. All right. Let's see. Nope, nope, nope. All right, that's it. That's it. No idea. No idea. Let's check the result. Damn. Well, we can go take a look at the hints and see if we have any hints on this. Similar questions. Serial topic. Dynamic programming. It is dynamic programming. So I think this probably is right. You just go through, but have you done this before? Nope. 3 round answers. DP. Yeah, it's knapsack. Exactly, it's knapsack. I know it's knapsack. Dedicated to beginners. Sure, DP. Okay, let's just what's the criteria? Like we know, I kind of know how this one goes, right? We know that we just we put each one and then we try to swap, but I don't know what criteria we need to choose in order to swap. Give us some. Give us some. Give us some. Man, that is so short. We could either build up DP table. Yeah, we can build up DP table. Okay. The maximum number of strings that can be formed with I zeros and J ones. It's updated. We should be able to add on from the previous iteration. From top left to bottom right, we'll be using results from this iteration. I don't understand what that means, but that's fine. That's it. All right. So we do get the maximum number of strings that can be formed with I. What's I and what's I and what's J? The maximum of strings that can be formed with I zero. Oh, I think it's thinking in reverse. So instead of finding how many can be formed, hold on. So what it's talking about is instead of finding how many, like what type of strings can we put together to fit the given requirement, what we now thinking about is given M and N, how many strings can we fit into it? But we're changing M and N instead of changing which string you're going to put in. That is interesting. Very interesting. Okay, so I'm okay. Okay, hold on. I have one more thing. I have one more thing that I want to see. I have one more thing that I want to see. Like you said, we failed on this one, right? The last one we failed. I just want to see like how. Oh, we did pass 27 test cases in this ridiculous solution. Output is 1. Answer is 2 because wait, these two? 1, 2, 3, 4, 5. Nope. 1, 2, 3, 4, 5. Oh, these two. How? The impact. Oh, this impact is really, really low. These two impacts are both very low. And this impact is really high. So we cannot, yeah, this is not working. The impact idea is not working. We did reach, I just didn't reach it. All right, so we're going to rethink about this, but I'm not going to look at this, try to code it ourselves. So we have m and n, right? Let's go back to the basics, to this one. No, I don't like this one. Let's go this one. Oh, it's 6 and 7. That's too big. Let's go to this one. So I have 5 and 3, right? So let's say we have 5, so it's going to be 3 and then 4 column, right? So basically that's saying we actually have to add one more because I have 0. That is 0 based. So we have 0, 1, 2, 3, that's on the M, and 0, 1, 2, 3, 4, 5, that's on the N, right? Oh, I got it. I got it wrong. Shoot. M, so it's going to be 6 rows and 4 columns. 2, 3, 5. 1, 2, 3, 4. Okay. So we have 0, 1, 2, 3, 4, 5 rows representing M. 0, 1, 2, 3, 4. No, 0, 1, 2, 3. I'll draw one more. 0, 1, 2, 3 that represent N, which is N columns. So M, so 5 zeros, 3. So what we want is to find how many, right? How many strings can we fit into all of them? So the one we want to look at is 5, 3, right? 5, 3 is the one we want to look at. This is the answer, 5, 3. But to get 5, 3, what we want to know is, let's go like build us up. Do we know 0, 0, 0, 0 is 0, right? 0, 0 is 0. 0, 1, on the top and on the first column and the first row, there's all zeros because we know that the strings contain at least, actually that's not 0. We have to go through them to find out. A 0, 0 is definitely because the string length, so 0, 0 is definitely not good, but 0, 1, 0, 2, 0, 3 is definitely possible. Okay, so let's go through it. What we have is so 1, 1. So the maximum to reach 1, 1. This is actually, we need to calculate it. Okay, so these are not zeros. We don't know what they are. So how do we calculate 0, 0 is 0? Right? How do we calculate 0, 1? So we have 0, zeros and 1, 1. Right? How do we calculate it? Well, we know 0, 0. So 0, 1, right? We have 0, 1. We want to know 0, 1. We can calculate 0, 1 based on, so 0, 0, 0. So if we know how many there are for 0, 0 and how many there are on 0, 1, then we know about 0, 1, right? The numbers that 0, 1 has. Like how many strings that is 0, 1, right? How many strings that's 0, 0 plus how many strings that's 0, 1 will give us 0, 1 because that's the only possibility to get to 0, 1. So we do have to go through this and just put in this table. That's just like the starting point that it contains 1, right? So okay, so we're gonna do 1, 1 is gonna be 1. Next one is 3, 3, 1. So 3, 1, that's going to be 1. 2, 4. Oh, I think you got it wrong again. M is, no, 2, 4 is not in it. 2, 4 is not in it. 0, 1, so 0, 1 is 1. We have 0, 1. And I have 1, 0, so 1, 0 is also 1. So this is our starting point, right? Starting point. And we try to fill out this table. So 0, 1 has to be 0, 0 plus 0, 1. So 0, 0 plus 0, 1 is 1. 0, 2 has to be the maximum that's can form 0, 0. And the maximum number that can form 0, 1. So it's 0, 0 plus 0, 2 or 0, 1 plus 0, 1. Oh, I still don't know how this DP working. Like 0, 0 plus 0, 2, right? So that's that. And also, so either 0, 0 plus 0, 2 or 0, 1 plus 0, 1. How do we do 0, 1 plus 0, 1? 0, 1 is the maximum number of strings that we can fit in the 0 and 1. And we want to know maximum number that can fit in the 0, 2. Even though I know, I read a solution, I still don't understand. The maximum number that can fit into 0, the maximum number that can fit into anything, right, into anything, equals what? The maximum number that can fit into, it should be the maximum number for 0, 2, should be the maximum number that can fit into 0, 1 plus the number of strings that, plus the number of strings that is 0, 1. Shouldn't it be like smaller or equal to? The maximum number that can fit into 0, 1. So this would be everyone, right, including 0, 0 and a 0, 1, right? And the maximum number that can fit. Put all of them in. And then we say the maximum number that can fit into 0, 2, it should be the maximum number that can fit into 0, 1 plus the number of 0, 1s that's not used in 0, 1, right? The maximum number that can fit into 0, 1. It's 1. The maximum number that can fit in 0, 2, we have 0, 2. What is 0, 2? It's like this 1, 1, right? Or 1 and 1. That should be, no, not good. I got stuck again. Okay, what is this? Count number of zeros and ones in current string. Okay, number 0, number ones, and then count the number of zeros and ones in a current string. So for each string, I know its number of 0 and number of ones. And then this is the maximum string that can be formed with I zeros and I ones and J ones, right? From the first few strings up to the current string. Go from bottom right to top left. If a cell in the memo is updated, we should be adding 1 to memo from the previous iteration where we are not considering as. If we go from top left to bottom right, we will be using results from this iteration, which leads to overcounting. Okay, this is the maximum number of strings that can be formed with I zeros and J ones. Okay, so the maximum number that we can form using 5 and so the maximum number that can be formed. Let's think about it again. So for each string coming in, we want to update this table, right? This table tells us the maximum number of strings that can be formed by n zeros and n ones. So let's say we have this table already, and then we have a new string coming in. I have a new string coming in. So we search through this table, right? We search through this table. For each one, we try to see if we can fit, right? Isn't that what we're trying to do? So each one we're trying to see if we can fit. That's a different idea. So previously I was thinking, if we know the maximum on a cell, we want to find out the maximum on the next cell, which I got stuck because I can't, right? You cannot know if we have maximum on the previous one, like what do you mean on the next one? So no, that's not a way to think. The way to think is we have m and n, which is to give us the maximum number of strings that currently we have locked already. So currently we have locked already the maximum number of strings that can be fit into an mn cell. Now we have a new item coming in. What we want to see is whether this string can be put into any one of those cells, right? So we say, yeah, if it can be put into that cell, then we update the number in that cell. If it cannot be put into that cell, then we do not update. Now, how do we know if it can be put into that cell or not? Now we know the number of zeros, number of ones, right? So apparently, but we don't know how many, so this table doesn't store how many zeros and ones has already been taken. Which we can, yeah, if you think about it, it is possible, but it's just wildly inefficient, because at each cell we need to store all possible combination, all the string that has already lived there, and we need to just do the swapping. Yeah, do the swap, not really swapping, because we want to know the maximum, right? But there's still the problem, like, do we swap or do we not swap under each situations? No, but that's not how it is. How it is if we are at a certain cell, right? Then we want to know whether we can put this in. I still don't know. I still don't know. What do? We do maximum memo itself and memo I minus this 0, j minus 1s plus 1. That means given our current ij, what we want to find out is the best situation. This is exactly the best situation, right? The best situation is if we know the maximum number of strings that can be formed in this condition, right? In this condition, and then that's the optimal, because we add the current one into it, that fits perfectly. That's the optimum. So we look for this. We look for this. I minus the current number of zeros, yes, and I minus number of ones. So this one gives us. So like if we have 5, 3, right? If this is 5, 3, and then our current one is 1, 1, 1, then we need to know the maximum number of strings that can be formed in 4, 2, right? If we know the result in 4, 2, then we can say we add our current one, then we can accept, right? We know this, then we know the maximum in 5, 3 will be the maximum in 4, 2. Yes, this is trying to say I want to add each string, right? I want to add this current string into this, right? I want to add the current string into this thing. Yeah, I want to add the current string into ij. I want to add it into ij, right? But in order to add it, we need to create room to add myself. And the only way to create room is to find a situation where I can just fit in, right? I can just fit in. And then we do this. Oh, wow. Wow. No, I will not be able to come up with this myself. Is this the basic idea of a knapsack? Uh, two knapsack. Yeah, I know this is a knapsack. How above approaches work. It's pretty similar to two knapsacks. The first solution gives TLE and put easy, just so you can understand. All right, let's find another one. I think one says it's a knapsack. What does 0, 1 knapsack mean? Pick several strings and provided strings to get the maximum number of strings using limited. Then create a three-dimensional array. Ooh, means the maximum number of strings we can get from the first I using limited j numbers and k numbers of ones. Okay, I don't understand. Which this means the maximum number of strings we can get from the first I argument string. Like the current I or discarding the current string. To result number 0. Oh, what the heck? Treat a larger one. We cannot decrease, but we can decrease the space complexity. Hold on, I still. So what are we doing here? This is for each. Uh, um, I have a better explanation. I still don't understand. Because no, we have to know knapsack. Knapsack is so common. The maximum strings we can include when we have x0s, y1s, and only the first k strings. Okay. Okay, only the first k strings. Only the first k string. That's what this means. Only the first k string. So it's 3 levels, right? It's 3 levels. So we have x and y, xy changes, and k changes as well. So the maximum strings we include when we have x0s, y1s, and the first k string. So to find this, we need to find the maximum between the same xy with k minus 1. That's right. Whether include or not include. This is where it comes from, whether include or not include. Yes, that's correct. I do have that memory, whether we include or not include, right? But my idea is if I include, that's easy to see. If I don't include, I go through the previous solution to find which one to swap. But actually, that's not considering all situations. To consider all situations, we go this. This is all situations. When we do not, now it's actually slightly different, right? Slightly different. This is a situation when we do not consider. All right, so this one is we do not include. And we do not include the current. This one do not include the current one. And this is we include the current one. Then we have to find the one. So that is knapsack. We probably need to search for knapsack as well. I mean, it's just like I don't know knapsack. I mean, I know how like it generally is, but yeah. Okay, so let's code it ourselves. Let's don't look at it. Code it ourselves. So yeah, it's this three. It's a 3 level, right? 3 level. First level. So we're gonna say DP, right? So the first. What's the first level? First level is the number of strings. So we're gonna say for this in range length strs, right? Actually, let's just do +1 as well. And then this, right, the second level is going to be m and n, right? We're going to say it's going to be 0 times, so n columns, let's do n plus 1 columns, right, for this in range n plus 1, right? So this is our DP, and we're gonna go through each one, right? For each letter, actually we don't need this anymore actually, so we can just say for I, S in enumerate strs, right? Then we decide whether we want to add this or not. That's actually +1. Right, we want to know from m and n right, from m and n, actually we can play a trick here. I can say start equals 1. I'm going to play a trick here. So we just say we're going to loop through m and n, right? Loop through m and n, and if it's negative, then we haven't done it yet, so it's going to be 0, right? It's going to be 0. So, but if it's 0, we won't add it. So we know its number of ones and its number of zeros, and it's either we don't add it or we add it. So it has to be, actually it has to be negative something, right? It has to be negative, like a negative infinity. Report math, I think it has to be negative infinity. Math.inf, right? Because the ones we haven't done, we don't know its value yet. So if we don't know its value, it cannot be 0 because 0 will be picked up, right? And if one of them that cannot be, what if I encounter one that can be, and it's a negative infinitive? No, it has to, like it will be 1, right? Then we have to eliminate situation where this gives us, like, you know, a 0 value, right? A 0 value. We cannot do 0. We have ones equals s.count 1. We have 0 s.count 0, right? And then we're going to say for m, for, right, for, oh, we have I already. All right, for P and Q. For P in range M, actually it's not gonna be M. It has to be the number, so it'll be 1, so M plus 1. And for Q in range 1, N plus 1, right? So we have PQ. Now we have P and Q. So for each PQ, we're going to try to fit the current one, right? And we say if P is larger or equal to 1s and Q larger or equal to 0s, that means we can fit, right? That means we can fit at least one. So we say, right, dp I, right, dp I P and Q shall equal to max, either I don't include it, so it'll be dp I minus 1, P and Q. So this is I do not include, or I include, which is dp I P minus 0s and Q minus 1s, right? This is, and then plus 1, right? This is the one I include. After I include, and that's it. We're going to return. Final result will be dp len strs, right? Len strs and m n. Okay. Oh, why is it not correct? What did I do wrong? That's weird. I don't know. I think I followed everything. P is going to be, yeah, from 1 to M. Q is from 1 to N. And we say if P is larger than 0 or 1, oh, P is 0s, Q is 1s. And that is when, yeah, let's try it again. Now we pass some and we fail some. Very interesting. I 1s and 0s, right? Then P is 1, P is 0s, Q is 1s. If P is larger than that, then we do. Oh no. Do we dare examine this? DP? No, this is not helping at all. This is not helping at all. It gave us 7. Okay, I minus 1. Did we pass the second one? If we didn't pass the second one, we're going to use the second one to check. No, we didn't pass that. I'm going to use the second one to check. All right, let's check. Let's check this second one. Okay, this one DP is more manageable. All right, so okay, let's try draw it out. Draw it out. See where the problem is. So we have 3, right? So we're gonna be a 3 level. So the first one is going to be 0, 0, 0, 0. And then when the first one comes in, right? First one give us 1, 1. And we say PQ, and then so DP let's actually do, let's say for mat in DP, print mat. Alright, so we get 1, 1 is 1, yeah, because we can put the first one 1, 1 into 1, 1. This is 1, 1, and the second one comes in. Right, second one comes in. I say second one is gonna be 1, 0, right? 1, 0, and we fit on 1, 0. They're gonna start from 1. Yeah, 1, 0 fit. So we say we're gonna try 1, 1. Should we start from 0? I think that is the problem. We should start from 0. Start from 0. Nope, this is 0 still not right. But we should start from 0. Start from 0, so 0, 0, no, we cannot do 0, 0. Coming back up, so we have 0, 1. No, we cannot do any of these because it's 0, so we have to go 1. Right, 1, 0, we can do 1, 0. 1, 0 should be 1. Yes, 1, 0 is 1. And 1, 1. Again, 1, 1. 1, 1 shall be... Oh, I think I know. The plus 1 should be here, right? Instead of this. This is previous one. No, 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 no. No. That's correct. This is previous one is 1. And then P minus 0 is going to be 0, 0. That's 1. So this one is 1. That is correct. This one is 1, right? This one is 1. That's correct. This is the last one. Last one by itself I have 1. And when we hit here, that's a 1, 1. Right? 1, 1, it's either, so that's 0, 1. Last one is 0, 1. So it should be 1, 0. 1, 0. Should it be minus 1? Right? The previous. This is previous, but do not include. This is a previous, but we're going to include current. Then we pass. Makes sense now. Now I think we shall pass. We still don't pass. My God. What did I got wrong? Yeah, minus 1. PQ plus 1. Minus 1 PQ. What is the issue? I honestly no idea. Like, do we not include this? If we don't include this, then what we're saying is the current, either I don't include it or, and then, wait, do we say we don't include this? I don't think it's going to be correct. Yeah, no, we have to include. But if we include, it's still not right. And we pass some, but we don't pass the others. No. Give me some more. Give me some more solution. I didn't do this one. Huh. If it's larger, that means I can fit. If it's smaller, that means I cannot fit. Which means that might be the reason. That might be the reason. So if it's smaller than 0, that's smaller than 1, right? That means I cannot fit. Then it shall be extending from the previous one, right? Shall be extending from I minus 1, PQ. Actually, I cannot add. Ah, that is the trick. Here is the trick. Huh. Now it makes sense. Yeah, we don't have to do all this. It's a knapsack. Yeah, this one shall be correct. Let's write some comment here. I know that this is a knapsack problem, but I don't know. I don't remember how knapsack is solved. I should, but I just forgot. I just couldn't remember. I just couldn't remember the algorithms that I have seen before. Anyway, even after I have read through the solutions, I still struggle tremendously putting together this solution. The intuition is to tabulate all possible combinations of m and n and find the maximum number of strings that can be formed, that can fit into each combination of m and n from the first to the ith string. Yeah, I hope this makes sense. From first to the ith string. Then, for any new ith string, trying to fit into p zeros and q ones, we choose the max between these two. One, add, do not add the ith string. Then dp I p q equals dp I minus 1 pq, right? Because we do not add the current string, so it's the same as the previous one. 2, we add the ith string, right? And then dp I 1 I p q equals dp I minus 1 p minus zeros q minus 1s plus 1. This is to find the best situation to fit the current string. The catch for me is that when a string does not fit into P and Q, we should extend dpi. We should do dp pq equals dp I minus 1 pq, which essentially says we cannot include the current string. Yeah, that makes sense. Runtime will be O and KMN, right? KMN, where K is the length of the input strs. Okay. Yeah. I think this one, if I keep pushing, eventually I will hit like a 5-hour mark as well. I'm pretty sure about it because I have nowhere. I did not go anywhere. I don't know where to go. Don't tell me this one times out. Yeah, it does not time out. I think it's just the internet is slow. Yeah, it's the internet slow. Hit 5108 milliseconds, or 21% ranking. This is like meaningless for this one. This one basically just the question itself, whether you understand. But people do very well. How? Huh. DFS. It's the same idea. It's the same idea. Okay. So, well, we passed this, right? But it's not on us. It's not on us. We're gonna put this in the. We're gonna grow this list really quick. Like this list is gonna grow really quick. We have so many questions that we don't know. Yeah, it's pretty bad. All right. Anyway, I'm actually gonna keep reading. I want to go to the knapsack and just get to know it a little bit better, so we have a better understanding of it. I probably will do knapsack right now, just kind of refresh the idea. All right. Anyway, that's it for today. No hard feelings that we didn't do it, but it's fine. Knapsack is important, and we went through it again. Hopefully, in the future, when we identify that a question is knapsack, we have an idea of how to handle it. This is basically just we don't know how to handle it. Like no clue. I know it's knapsack, but I forgot the algorithm for knapsack. If I know, I think I will be able to figure it out. Yes, I think if I know, I will be able to figure it out. All right, that's it. See you guys tomorrow. Adios.